Hello, everyone. Welcome to our Deep Learning Design Pattern Study Jams, Session 3. I am Margaret Maynard-Reed. I'm the lead organizer of GDG Seattle. And today we also have Anchi joining us, another organizer. And we have Andy as well, the main instructor of the study jams. And for those of you who are new to GDG Seattle, we are an inclusive community where everyone is welcome. Our motto is be excellent to each other. If you see or experience anything different, please contact the GDG Seattle organizers. So today we're going to just have a brief intro of the instructors, and in case some of you who are new, and then we'll look at the list of the topics that are for session 3. And after that, we will open up for Q&A and then wrap up for today's session to talk about your homework for session 4 next time. If you have any questions, please feel free to post it on YouTube live stream, and we will add it as a banner to this recording and then answer the questions. In the meantime, if you could just copy the same question to that Google Doc, it would be great. That way we can see a full list of questions that's being asked for each session. And feel free to use the hashtags below and follow Andy and I on Twitter. So here is Andy.
All right. Well, hello, everybody. First, I want to say thank you for joining session 3 here. As Margaret said, I'm Andrew Ferlitsch. I'm part of Google Cloud AI. I belong to developer relations. If you're not previously familiar with me, I'm typically at conferences. I might be at a university acting as an adjunct professor, do presentations at meetups, training and workshops, and I spend a lot of time with Google's enterprise clients. My expertise is in computer vision and deep learning. I was formerly a principal research scientist specializing in imaging for 20 years, and I have 115 US patents based on my research. And I'm writing a deep learning book to be published by Manning. So I'll turn it back to you, Margaret.
Thank you, Andy. So as I said earlier, I'm the lead organizer of GDG Seattle. I'm also a Google developer expert for machine learning. I also organize meetups for another group called the Seattle Data Analytics and Machine Learning. Currently, I'm a machine learning engineer and a researcher working on AI for art and design. I don't have a slide for Inchi, but I think we should have Inchi talk about who he is as well. Make sure we add a slide for him. So, Inchi, a bit about you.
Hi, I'm Yanqi, one of the GDG organizers. I'm helping out with this event. I am currently a software engineer working on Android and tap a bit of my toe into ML as well. So, yeah, nice to be here.
Yeah, thanks, Yanqi, for helping. Okay, so Andy, back to you.
Okay. So, this for this session, what we asked you to study were these 4 parts here. We first introduced you to design patterns for models and showed you the idiomatic procedure reuse design pattern. Okay. And then we showed you sort of how to apply it to different early state-of-the-art models. And we then went in, and most of those models went deep. And then in the next section, we talked about state-of-the-art models that tried to improve accuracy and performance by going wide. And then other state-of-the-art models that used other alternative connectivity patterns that were neither deep or wide. And then we wrapped it up with the patterns, or the mobile design patterns that are used for mobile convolutional neural networks that have to fit into that smaller footprint of a mobile or IoT device. Okay, so it's a good time for some questions. I know there were some on the Dory, so I'll just go ahead and start with those. Okay, so the first question here is somebody was asking, when they're stacking layers and you get deeper and deeper, we tend to do that downsizing or pooling. Okay, so the feature maps get smaller and smaller the deeper you go in. And they were wondering what happens when you get down to 1x1 feature maps. They're saying at this point it kind of looks like it's just the same thing as a DNN. They weren't sure, did it make any sense to be stacking feature maps of 1x1? And in a sense, they're right. Convolutional neural networks are designed knowing the input size and the amount of reduction. And when you get to the very end, before you get to the back end, what we call the bottleneck layer, and you flatten, ideally, the feature maps never get smaller than 3x3. So they're 9 pixels or more. Any smaller than that, they've lost too much spatial information and the model isn't going to learn. The next question somebody asked me, they were wondering about the loss function and how, it's not clear. It says, does it have to be manually trained with humans using a CAPTCHA system or something? No, a loss function is just a mathematical function. It's a predefined function. And it's just your way of calculating how far off are you from the ground truth. So let's use a simple example like a regression. You're estimating, you're predicting the price of a house. And so you have, what the real value was, let's say it was 100,000 and you predict 90,000. So you got to calculate a loss. What's the difference between 90,000 and 10? Well, one way is you could just take the absolute difference, and that would be 10,000, right? Okay. But in regression, we actually use the root mean square error, okay, which means that you would actually take the square of that difference, so 10 times, and then, how do I say, and then take the square root. And what that does is it penalizes the further you're away, okay? And so every different task that you're going to learn, whether it's regression, classification, or object localization, etc., researchers over time have found the loss function, the statistical loss function that works best for models to learn that task. So I'll pause for a moment and see if we have anything on our live comments. Not yet. Okay. Feel free to ask comments about my answers if you'd like to, if you want to dig deeper.
I just want to add a bit to the question as well as the answer. I added the banner to the screen. The question was actually not only how loss is determining tuning a function, but also probably a model. Also, the question was it automatic or manual? And I think, Andy, you answered the question in terms of different types of loss functions, right?
Yes.
But we also want to address, why do we need a loss function, right? I mean, the whole purpose of the machine learning is that you have the data and, say, supervised learning, say, image classification. You have the images and the labels, and you're trying to figure out this model, which is kind of like a mathematical function that can be used to predict for other future new images, right? So the purpose of the loss function is actually try to make that new prediction as close to the whatever the label you gave us possible, right? So to answer the question if it's automatic or manual, I don't think it's manual human there trying to get that loss. It's actually a function that you define.
It's a static function.
Yeah.
A human
model you calculate differently.
But it's a static function. So maybe I could better explain it. So every time you're training and every example, and let's say is an image, you're going to try to compare how close is my predicted image to the real image. And that difference is a function, and we're going to call that the cost. But you did a batch. You did, let's say, 16 images. And so you have 16 cost values. And somehow I want to add them up to be a loss. And I'm going to apply some function. Okay. And whatever that number is, I'm going to use it to backward propagate through the model and update the weights. And my goal is every time I want to make that loss smaller. And when it gets smaller, then my updates on my weights get smaller. And that means they're getting closer and closer and closer and closer. So if you're training and you see your loss going the other direction, that's a bad thing. You're not learning. You want to go smaller, smaller, smaller.
We have a question on chat.
Okay. When we are defining the convolutions, we should start defining the kernel size, increasing or decreasing across layers. In most models nowadays, we pretty much use, except for the very first convolution, we might use a coarse filter, filter size, kernel size. It's the same thing. Okay. You might see a 7x7 or a 5x5 as the very first convolution, but typically every other convolution after that is going to be a 3x3. Occasionally, as you study the material I gave you, you'll see that there are 1x1 convolutions, but they do special things. They're about either expanding the number of feature maps or pooling the number of feature maps. So they're more about upsampling or downsampling, or in other words, increasing dimensionality or reducing dimensionality, not feature extraction. Most feature extraction today is done with 3x3 kernel size filters.
So I just want to add a bit, like, thanks for asking the question on the live stream. I feel like if you ask the question very short sentence, it's very easy for us to add it as a banner on the screen, since we don't really have a presentation that we're giving. So it's kind of nice to see that question on the screen. But I understand it's kind of double work, but it's also nice to keep track of, especially your detailed question in the doc. So either way.
Okay. So here's another question I see in the door that kind of goes along with the loss. I think I'm a little bit lost somewhere between the basic terminology and the architecture discussions week 2. I'm not sure how a simple classifier working on something like mints would be able to know the right or desired features from the wrong ones to make progress. That's what the loss is all about. Okay. If my model is making the wrong features, let's just call them, okay, what I predict is going to be a long ways away from the ground truth, and my loss is going to be really large. And that means that when I'm going to backward propagate, I'm going to make big changes to the model to try a different direction. But if I'm actually predicting stuff that's, quote, the right desire features, then what I predict is going to be really close to the ground truth. My loss is going to be really small. And so the updates to my weights are going to be small. And I'm basically just honing into the perfect values or the optimal values. Never get perfect, but optimal.
I just want to add a bit about the terminology feature. I think the input data has the images and as well as the labels. And what the classifier is trying to classify is actually the class or the labels, not the features. The network learns the features from these image pixels. So that's just one clarification. There's also a question right above this particular question is, as I went through the video for week 2, it seemed like the designs expressed using Keras just use different permutations of various building blocks expressed with functions for dense versus convolutional network components. Are there rules of thumb for using different architectures in different types of application that can be generalized? I may be oversimplifying it. So that's another question, basically asking how are we using these building blocks and also different architecture in different type of applications.
Yeah, architectures are actually specific to the task you're solving. So the evolution, right now, we've just been showing you a single type of task, classification. And what you've been seeing in these videos is how researchers over time progress to a better and better and better and better architecture just for classification, how they redesigned building blocks and made new building blocks. In later sections, if we have a chance to, we'll talk about object detection. You'll see that the structure is different, the architecture is different, the building blocks are different. If we were doing image segmentation, again, different architecture, different building blocks. But once you know they found a really good architecture building block for a task, no matter what problem you apply that task to, generally that architecture will work well. It's more after that about the data set and the hyperparameter tuning. Do you want to add anything more, Margaret?
Yes, I do have something to add. So as Andy said, depending on what kind of task, you know, assuming we're talking about computer vision task here, you know, classification versus segmentation, object detection, etc., etc. You know, there's also more complex ones such as GANs, generative adversarial networks, etc., etc. I also want to point out that how you structure the network architecture not only depending on the computer vision task, but also the actual application it runs on, where your model is deployed to. For example, if your model is deployed to the cloud, you can afford to have a much more complex architecture with higher accuracy or better, you know, higher accuracy. But if you are deploying the model to, say, mobile or embedded, you want to have the model to be smaller in the size, but faster, run much faster, less consumption of battery, and, you know, also constrain the memory, etc., etc. In that case, you will structure your architecture to be simpler, and that's actually Andy for session 3. One of the videos Andy made is on the mobile net, right, Andy? And that's one of the networks that for you to run on small devices.
Mm-hmm. Yeah, so originally these architectures were being designed for the ImageNet competition. Okay, and these are 1 million images. They're sized 224 by 224. It was a very competitive environment. Everybody wanted to be a winner. So neural networks convolutional neural networks, these state-of-the-arts got bigger, 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 or more or less deeper, deeper, deeper. Well, they got so big, you can't put them on what we call a memory constrained device, you know, like an IoT device that has a small memory footprint. Okay. And so the whole thing about mobile networks is they really had to redesign from the bottom up architectures that would get okay performance. If they're not huge, they're not going to get the same level of accuracy, but reasonably good accuracy, but be able to do it in a small footprint. So they were trying to, instead of maximizing the accuracy, trying to minimize the footprint.
Yep. So it's a trade-off you need to make a decision on based on your application. So next, there are a couple of other questions. I am going to put it on the...
Yeah, we'll maybe we should go to here to the live comments and then come back to the Dory again.
We answered this one.
Oh, okay. Thanks for catching that.
Yeah, and I think the next one by Ari, he's just noting that we answered it.
Okay. Sorry, I'm focusing on just click on that show and hide. So I'm actually not reading it.
Okay. So there's one about Amos about what happens if you're training with blurred images or complex backgrounds. Does that affect the performance of the CNN network? Sure. It really depends on sort of the whole makeup of your training data. I'll go into it. It's called a distribution and what your application is. But let's say your application is it looks at things dead on in a really crisp environment, and you're training with blurred images, you probably not going to work. On the other hand, if you're putting this in the wild, then it arbitrarily sees things that say the pictures are taken by people's mobile cameras, different angles, different times of the day, different resolutions, then, you know, it might be helpful to add some blurred images, okay? Some randomness or noise in your data set we call regularization, and it actually helps models generalize to data it never seen when it was trained. As far as complex backgrounds, actually, the more complex the background is, the more likely the model will learn it's not part of the image you're trying to recognize. Okay, and I'll give you a simple example. Some of you probably have already heard this old story about wolves, a model somebody had trained for wolves versus dogs. Okay. And the problem is when they trained it, all the pictures of the wolves, the background had snow in it. And so when they made predictions, if there was snow in the background of a dog, it said wolf. Okay. What the model learned was snow was a wolf. And that's because of the uniformity of the snow in the background. If instead that background had been really complex and mixed up in that, it would never have learned that was part of a wolf.
Great. Thanks for the answer. Do we have any other questions?
Well,
I
think there is. Oh,
yeah, we skipped the question by Dennis about the convolution network.
From the doc?
No, from live comments.
Oh, okay. Let's go back to the live comments. Can you highlight it?
What's the question?
General convolution network question. From prior videos, I've seen several examples of how neural network solves classification and categorization problem. What about things like time series?
Oh, yes, we did.
Okay.
Okay, so we don't really cover time series in this series because we're talking about image, mostly image classification. Okay, but time series are solved through what are called recurrent neural networks. Okay, or RNNs. I don't know. Do you want to say something about it, Margaret? It's not really my specialty.
I would say like our study gem, this study gem session. This series is more focusing on computer vision, but yes, definitely you can use deep learning for time series forecast. Okay, I think I'm going to jump back to the doc. There's a question on session 2, part 4, mobile.
Yeah, I would think the answer to his question is he's correct. Or they are correct, excuse me. They're just asking, okay, there seems to be an evolution of CNN variants going from BGG, ResNet, et cetera, et cetera, et cetera. It looks like they're trying to find a better way with a combination of techniques, such as expanding and reducing the number of feature maps, projecting blah, 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 and preventing vanishing gradients, and and just say, is this a misleading impression due to your successful introduction slides? And no, I mean, that's exactly what researchers were doing. Whatever the last person did that was successful, they start with that and they see, what can I do next to even make it better?
Yes. So basically, I will say better in, sometimes it's the accuracy or, and sometimes it's the make the network run faster or smaller. So basically better architecture to solve.
So there are different goals people had for improving the architecture. One obviously was accuracy. The next one was how long did it take to train it? Okay, and then another one is what's the size of the network? What kind of device can I put that model on, and what will be the latency for making a prediction? So the bigger the model is, I put an input, the longer it takes to get to the other end. So it's a longer amount of time before I get an answer.
Yep. So
I think we have some more here.
live comments.
Yes, we have.
I benefited from the reminder that what we are doing here is building classifiers and other ML problems may have different solutions. Okay, that's just a comment. How do you debug a CNN, visualize feature maps? We actually can do that. So one of the things is, like I like to do is I can actually break I can take my model and let's say I have a bunch of layers, right? Okay. And let's take that last layer of feature maps and I like to know what it looks like. Well, I can tear off the layer below it and just use that as my output. Okay. And that's going to give me, let's say it's a 4x4, 16 pixels. Well, I can just go ahead and display that as an image and see what it looks like. Matter of fact, if I wanted to, I could actually add outputs of every layer. And while I'm training it, actually visualize the transition, starting with the real image and how it changes to the as I go down through the feature maps.
Yep, we can visualize the feature maps in each layer. There are different websites or just like collab notebooks that we could share on the visualization.
Yeah. And there are tools out there for doing it. I don't use them because I'm just used to hand instrumenting my own models. but most people would just use, an off-the-shelf tool to do it.
Yeah, I think it's good y'all asking these questions. If you also put all the questions in the doc, I will go through. Like if there's some other resources, I will post it onto the Study Jam Slack.
Yeah, I like the next question. Put a CNN in front of an LSTM. I think that's called attention. As in a BERT model.
So here's another question.
I don't really think the color representation, whether it's HSV or RGB, is going to make a difference. In most cases, what you're learning isn't even dependent on the color.
Sometimes background of the image matters, though. I think like the background of a particular.
Yeah, but even like in the case of, let's say, snow, which we think is white, if it's dim light, maybe it's going to look gray, right?
Oh, I'm not talking about the background of the actual image. I'm talking about whether the background is white versus transparent, like the image.
Okay. Yeah. Generally, if we want a neutral background, we have an image and we're going to just superimpose it on something and the rest is going to be one color. The best color is black because the value of that pixel is 0. And without going into detail, statistically, 0 times anything is 0, which means no signal.
Okay, great. So are there any other questions? We have about 2 more minutes.
Yeah, well, let's go check the Dory. No, I don't see anything new there.
Okay. Well, if not, I can just move on to the next slide because I think if you all have any questions, please join the study jam.
One last question.
Oh.
From where?
From the live chat. Is image segmentation a big topic? Will it be included as extension chapters?
It won't be we're certainly down the road. I'm writing chapters on it as far as my book, but as far as this study jam series, we're only doing image classification.
Yes, it's a big topic, segmentation. Right. It's quite useful in the real world.
Yeah. I mean, first you have to learn what, here we're doing a single task model. You have to learn what a multitask model is. Then you got to learn about object detection and the stages in it. And then finally, on top of all of that, you learn how to do the image segmentation. So it's a buildup.
Okay, great. I think that's all of our questions for today. I'm trying to move forward. So, I'm assuming some of you are new to this. Actually, who is all new here? Raise your hand or
in live comments, yeah.
in comments. Like, who's new?
Is everybody here a returnee?
Anybody who's like the first time joining? Anyways,
many of these names I recognize that are asking questions from
for those of you who are new, I again, here's how you study. You read Andy's deep learning primer and all the materials on GitHub, and then watch the videos, do the exercise, which is in Colab, and then make sure you join the Slack channel to help each other out and ask questions. And then bring your questions to study gym sessions for the live Q&A like today. And oops.
Oh yeah. So back to me. Okay.
Yep, you.
So for our next session, we're gonna move forward now. So far we've really talked about first kind of introduced you to neural networks and then introduced you to convolutional neural networks and sort of some foundational work with DGG and then the residual network. Okay. And then we went deeper. We talked about the evolution of them, going deeper, going wider, alternate patterns, and then optimizing them for mobile devices. So now we're going to sort of go into some new areas. So we're going to introduce you to a new type of model called an autoencoder. When you study that section, you'll find that you can use autoencoders from things like compression, super resolution, denoising. So it's a totally different task. You're not predicting anything. You're actually taking your input, the image, and modifying it to be something else on the output. Okay. And then another thing we've talked about, you've already heard a lot already, is, your training is a lot to do with your data set, but it's also a lot to do with how you train with that data set, the parameters that you use, and we call that hyperparameter tuning. And so you'll be covering that. And then finally, you're probably familiar with the concept of transfer learning. So today we got a lot of great models out there that have been trained on massive amount of data. And what we have found is that you can kind of relearn what they already learned and adapt it to a new problem. So you don't have to train from scratch. So we'll also be covering transfer learning. So go back to you, Margaret.
Yeah, these are very interesting topics, I find. So after today's session, I will again put the slides on Meetup as well as on the YouTube recording so that you have the links to all of these for studying for the next session. And, I hope you all had fun today with our Q&A and have fun studying, and we'll talk to you in 2 weeks. Bye, everybody. Thanks for attending.